So, what if I told you that you could use something as simple as electricity to literally tear molecules apart and then build brand new things atom by atom? Well, it's not science fiction, you know? It's a process called electrolysis, and believe me, it's happening all around you. Okay, let's just dive right in.
To get us started, let's think about a question that sounds a little bit like magic, right? How can you take a totally plain steel spoon and give it a perfect shimmering coat of pure silver using nothing but electricity? We're going to unravel this mystery together, and by the end of this, you'll see exactly how this little piece of everyday alchemy is totally possible.
Okay, to understand how this all works, let's think of electrolysis kind of like a play. And you know, every great play needs a cast of characters. So let's meet the key players on our chemical stage.
First up, we have the stage itself, the electrolyte. Now, this is a special kind of liquid, either a melted salt or a salt that's been dissolved in water. And what makes this liquid so special? Well, it is just buzzing with charged particles called ions, and these are the real stars of our show. Without them, nothing happens. It's just a boring liquid.
Next, let's meet our first lead actor, the anode. Think of the anode as the positive character in our play. And you know what they say, opposites attract. So it draws in all the negatively charged ions. Its one and only job, to snatch electrons away from those ions. In chemistry, this process of losing electrons has a name. It's called oxidation.
And what's a hero without a counterpart, right? Meet the cathode, the negative electrode. And following that same rule of opposites, the negative cathode attracts all the positive ions. Its role is the exact opposite of the anode's. It gives electrons to the ions that come its way. And this process of gaining electrons is called reduction.
You know, what's so cool about all this is the perfect symmetry of it all. As you can see, the anode and cathode are perfect opposites. One's positive, one's negative. One attracts the negative ions, the other attracts the positive ones. One causes oxidation, that's a loss of electrons, while the other causes reduction, a gain of electrons. It's really just a perfectly balanced chemical dance.
Okay, so we've met the players. But with all these ions floating around in the soup, how in the world do we predict what actually gets made? It might seem a little chaotic, but here's the cool part. There's a simple set of rules, kind of like a cheat sheet, that lets us predict the outcome of any electrolysis reaction. So over at the negative cathode, it all comes down to a competition. Imagine all the positive ions in the mix, and if you're in water, you've got hydrogen ions in there too, right? So who wins? Well, the rule is simple. The least reactive ion gets the prize. For example, if you have both copper and hydrogen ions, copper is way less reactive. It's just more chemically chilled out, so you'll see a beautiful layer of solid copper forming on your cathode, not bubbles of hydrogen gas. Now let's look at the positive anode. Here, the rules are a bit different. You've got to check for specific negative ions called halides, things like chloride or bromide. If you've got a whole bunch of them in there, they win, and you'll get a halogen gas like chlorine bubbling off. But if there are no halides, or just a tiny amount, then the water itself actually steps in, and you'll produce pure oxygen gas instead. Simple as that.
All right, enough with the theory. Let's see this stuff in action. It's time to put our rules to the test. But hold on, there's one more crucial detail we need to think about, something that can totally change the game: the electrodes themselves. And this is a really key distinction. Sometimes the electrodes are kind of like the referees in a game. They're there to make the action happen, but they don't actually get involved themselves. We call these inert electrodes. But other times, they jump right into the game and become part of the reaction. These are our active electrodes.
And this slide shows that difference perfectly. I mean, look, on the left, those platinum electrodes are a great example of inert electrodes. Platinum is super unreactive, so it just provides a surface for the reaction to happen on. But look at the right. You can see the copper electrodes are literally dissolving into the solution. They are active participants, changing the chemistry of the whole system. So let's look at a classic experiment with these inert electrodes. This cool-looking device is called a Hofmann voltmeter, and it's being used to pass electricity through water. Those platinum electrodes aren't reacting at all. They're just acting as the positive and negative terminals to split the water molecules apart.
And the result? It's exactly what our rules said would happen. At the negative cathode, we get hydrogen gas. At the positive anode, we get oxygen. But here's the truly elegant part, and you can see it right there in the tubes. We collect exactly twice as much hydrogen as oxygen. Now that's not a coincidence. It is visible, physical proof of the chemical formula for water, H2O. 2 parts hydrogen, 1 part oxygen. That's science you can actually see.
But look, this isn't just a cool classroom experiment. The principles of electrolysis are the backbone of massive industrial processes that we all rely on every single day. So let's connect the science to the real world. And yeah, to those silver spoons.
One of the biggest and most important uses of electrolysis is making metals incredibly pure. I'm talking about the tiny bit of wiring in your phone, the complex circuits in your computer, the electrical system in your car. All of it relies on ultra-pure copper, and electrolysis is how we get it.
So this is how it's done. You start with a big, thick slab of impure copper as your anode. Remember, that's our active electrode. Your cathode is just a very thin sheet of already pure copper. And the electrolyte, that soupy solution, is full of copper ions.
Okay, here's the magic. When you flip the switch, that impure anode starts to dissolve. Copper atoms lose their electrons and just dive into the solution as positive ions. These copper ions then race across to the negative cathode, where they get their electrons back and plate on as pure copper metal. The cathode just grows layer by layer with 99.99% pure copper, while all the gunk and impurities from the anode just fall to the bottom as this useless sludge. It's brilliant. And that brings us to our second major application, and yeah, the answer to our original question: electroplating. This is the art of using electrolysis to put a super thin layer of one metal onto another.
This setup for electroplating is so elegantly simple, and it follows 3 golden rules. First, the object you want to coat, our spoon for instance, that has to be the negative cathode. Second, the metal you want to coat it with, in this case silver, must be the positive anode. And third, the electrolyte has to contain ions of that plating metal. So we need a silver solution.
And why do we even do this? Well, there are 2 big reasons. The first is just appearance, to make inexpensive objects look beautiful and shiny, like silver-plated jewelry or those chrome car bumpers. And the second is protection, coating a reactive metal like steel with a less reactive one to stop it from rusting.
And there you have it. The mystery is solved. You take a plain steel spoon, you hook it up to the negative terminal of a power supply to make it the cathode, you use a bar of pure silver as the positive anode, you dip them both into a solution of, say, silver nitrate, turn on the power, and you can literally watch as silver atoms travel from the anode through the solution and plate themselves in a perfect, shimmering layer right onto the spoon. It is that simple and that cool.
And that leaves us with a final, kind of mind-bending thought. We've seen that electrolysis gives us this incredible, precise atomic-level control. We can break compounds apart and stick pure elements exactly where we want them. So if this is what we can do today with something as fundamental as electricity, what does the future hold? What entirely new materials with properties we can't even imagine yet could we build from the ground up, one atom at a time? The possibilities, they're truly endless.